Welcome to this lecture. This is the third lecture of week 4. In this week, we are concerned with various properties of various modes of convergence of random variables that we have introduced in the previous week, namely convergence in LP, almost sure convergence and convergence in probability. In the previous lecture, we have looked at various nice algebraic properties of these three modes of convergence. In this lecture, we are now concerned with finite sums and their behavior in these different modes of convergence. First of all, we will concentrate our attention only to almost sure mode of convergence, and later on we will see their effect on these finite sums for the other modes of convergence, meaning for convergence in LP as well as convergence in probability. So, without further delay, let us continue the discussion with the lecture notes. All right. So, now what we are going to look at is that going to be given a sequence x n of random variables, all of which are defined on the same probability space, and then we are going to look at finite sums of these random variables specifically related to this structure. So, we are going to look at first n many of these random variables, add them up, and we are going to call it S n, and we are going to be interested in the large time behavior, meaning for large n how does S n's behave. Now, as stated earlier, we are going to assume that all these random variables are defined on the single probability space omega f p. Now, to handle this type of finite sums, first of all what we can do is that we can appeal to standard techniques from real analysis. In this lecture, what we are going to see is that there are very nice results from real analysis, which we can directly apply and get almost sure modes of convergence for S n. But later on in further lectures, we will use probabilistic methodology to get nice estimates for convergences involving S n. So, let us continue and see what are nice results from real analysis that we can apply in order to see their behavior for the new sequence S n. All right. So, first we are looking at techniques from real analysis. We start with lemma 1. This says that I start with a sequence of real numbers a n which converges to a real number a. Then what we can show is that a 1 up to a n, if we add them up and divide by n, meaning I look at the averages of this sequence, then it also converges to a in the limit. To see the proof of this, let us use standard techniques. So, without loss of generality, we will start by assuming that the limit is actually 0. This is not losing any generality, because we can always look at the sequence a n minus a, and for this sequence this is going to 0 as per our assumption. If we can show that a 1 up to a n is going to a divided by n is going to a, it is equivalent to the fact that a 1 minus a up to a n minus a divided by n is converging to 0 as n goes to infinity. So, therefore, we can always take the limit value a to be 0 and make our argument. Now, as long as the limit is 0, then given any epsilon positive, there exists a natural number capital N such that all the terms after the nth stage has this bound given by the epsilon, meaning modulus of a n is smaller than epsilon. But now, for all such large small n, as long as they exceed this level capital N, then we have this very nice estimate for the averages in question. Here what we can do, we first appeal to the subadditivity of the modulus function, which is essentially the triangle inequality that we are applying here. We first split into the first capital N many terms and the remaining terms, and we have taken 1 by n outside, that is not playing any role for the moment. Now, for the final terms, meaning after the stage capital N, I have this upper bound given by epsilon. Therefore, the second sum that we have figured out has this upper bound given by small n minus n divided by small n multiplied by epsilon. Now, the first term we have kept as unchanged. Now, we note that the second bound that we have obtained, that can be further dominated from above by epsilon. But now, note that this epsilon is arbitrary, and as small n goes to infinity, the first term on the right hand side is going to 0, because we only have a finite sum of terms here. So, therefore, as long as small n goes to infinity, the first term on the right hand side is going to 0, and therefore, that term also can be made arbitrarily small. So, therefore, both the terms on the right hand side of the star relation, which is the upper bound for all these averages in question, can be made arbitrarily small as we like by choosing the n large enough, and hence for all such epsilon positive we can make it small, and hence the result says that the averages must be small for large enough small n, and hence this will tell you that the averages are going to 0, and this we have proved by assuming that the original sequence is going to 0, which was stated without loss of generality, and therefore, the actual result will also follow. Now, this result can be directly applied for the case of random variables. So, as an application of this result, we see the corresponding version involving random variables. What we consider here is this, that there exists this sequence x n converging almost surely to the limit random variable capital X. Now, our claim is S n over n, that quantity converges again to the same limit random variable in the almost sure mode of convergence. Here you note that S n is actually denoting this finite sum of first n many random variables, and we are claiming that again the corresponding averages for these random variables are actually going to the same limit. How do you show this? We again appeal to the appropriate definition of almost sure convergence. We are having a set coming from the sigma field such that its probability is 0, and on the complement of this measured 0 set, we are having the pointwise convergence of this sequence, meaning x n of omega converges to x of omega. Now, if you look at this sequence of x n of omega coming from the complement of this null set, then pointwise by appealing to lemma 1 earlier, we will say that S n omega over n, that converges to x of omega as n goes to infinity, and this is true for all omega on the complement of this measured 0 set, and hence the result follows that S n over n converges to x in the almost sure mode of convergence. So, we have seen that a very elementary result from real analysis can be applied to the setting of random variables, specifically those related to the almost sure convergence, and this is going to give us that S n over n is converging to the same limit random variable as long as the original sequence was converging in the almost sure mode of convergence. But now, we recall another comment here, that S n is actually the sum of first n many terms, and therefore, S n over n actually denotes the sample averages, and what we have actually said is that the sample averages are actually going to the limit random variable in the almost sure mode of convergence. Now, what we are going to see is that this earlier elementary result from lemma 1 can be generalized further, and these more general statements can again further be applied to the case of random variables, and we will obtain other nice results involving such finite sums of random variables. So, let us see. So, here this first result involves again another such sequences of random variables, but we start with a double sequence, meaning here there are two indices I and j varying over the positive integers. We assume that for every fixed value of j, the limit of a I j is 0 as I goes to infinity, and by fixing I should also have that the series a I j as j varies from 1 to infinity, that series must be absolutely convergent. So, that is the assumption that we are making here. In particular, note that this will also tell you that the limit as j goes to infinity of the terms a I j must be 0 for all fixed value of I. So, that will be a necessary condition for the absolute convergence of the series here. So, here we are asking for this kind of a bound by a constant which is assumed to be positive. Now, if we assume these things for these sequences, this double sequence, then we are going to look at some specific structures involving other sequences. What we do is that we look at another sequence which we denote by x n, and we assume that the sequence is bounded. So, a priori we are not assuming any other conditions other than just that the terms are bounded by some constant. Then what we can consider is another sequence constructed out of x n and the a I j's that we had looked at earlier. What we will do is that we are going to look at these summations for every fixed value of n. What we do is that we observe that as long as these x j's are dominated by some constant, let us say capital R, then modulus of a n j times x j is dominated from above by R times modulus a n j, but then we assume that the sequence a n j's that gives you that the corresponding series converges absolutely, and therefore, using this absolute convergence we have that the new series that we are looking at here also converges absolutely, and therefore, we can look at the usual series and the sum of it we denote by y n, and thereby we obtain this new sequence y n. So, this is some kind of a weighted linear combination of the sequence x n, and the weights are given by this a I j's which are essentially going to 0 by fixing I or fixing j. Now, we are going to be concerned with the limiting behavior of these weighted sums which are denoted by y n's. So, what we observe is that these two following statements hold, that if the original sequence which we assume to be bounded, if that converges to 0, then the new sequence which is made up of these weighted sums of x n, they also converge to 0. And secondly, if the original sequence which we assume to be bounded is converging to some real number x, if in addition if we have summation of a n j's as j goes from 1 to infinity goes to 1 as n goes to infinity, then under this condition we can show again that the weighted sums which are given by y n converges to the same limit x. So, these are the two statements which we are going to show. So, to start off with, we assume that the new sequence x n's go to 0. Now, here as long as that happens, then given any arbitrary epsilon positive, there exists a natural number capital N such that after that stage capital N, all the subsequent terms are small, in the sense that modulus of x j must be less or equal to epsilon. This is just by the definition of the limit that x n's converge to 0. Then for all n, we can make this observation that modulus of y n, which is nothing but the summation a n j x j as j goes from 1 to infinity. If we apply the modulus function here, we will be having this upper bound for modulus of y n, which is given by this summation. First we look at the sum of first capital N many terms and then the sum of the remaining terms, and each of these can be further dominated by the modulus value of these terms. So, we have an upper bound for this summation, and now what we observe is that for large values of small j, which is after the stage capital N, we have this upper bound given by epsilon, and moreover summation of mod a n j's that has an upper bound given by small c. So, that is what we have written here, that this second summation here can be dominated by epsilon times small c. We keep the first summation here intact. Now, what we observe is that in this first summation, what happens is that as small n goes to infinity, then this finite sum we can pass the limit inside, and therefore, we can look at the finite sum of term by term limits. Now, in the term by term limits, by our assumption, this limit of the terms a n j's that is actually 0, and hence this whole summation is 0. So, therefore, this summation of finitely many terms as small n goes to infinity goes to 0. Therefore, from the double star relation that we have proved here earlier, we have an upper bound for modulus of y n, where the first term can be made arbitrarily small because it is going to 0 as small n goes to infinity, and the second term here on the right hand side of double star, that is epsilon times c, that can also be made small because epsilon is arbitrarily small. And therefore, from this earlier upper bound double star, we conclude that y n's must converge to 0. And hence, what we have shown is that as long as x n's converge to 0, the corresponding weighted sum given by y n's also converge to 0 as n goes to infinity. And then there is a slight generalization as is given by the part 2 of the statement. Here we have assumed that x n's converge to x as n goes to infinity, and therefore, x n minus x will converge to 0, and here we can appeal to the part 1 and claim that this series for over the index j will converge to 0 as n goes to infinity. Now, we appeal to this observation, and then we also recall that we have another assumption part of our hypothesis, and therefore, using both these things, one that the first limit is 0 and the second is 1, what we get immediately is that y n, which is given by summation a n j x j, can be thought of as this kind of a summation a n j x j minus x plus x times summation a n j as j goes from 1 to infinity. But this second summation here is actually 1, and therefore, what we ended up having is that as small n goes to infinity, y n, which is this addition of these two series, is actually having the same limit as this term here, and hence what we ended up having is that this can be split further in terms of these two series, and it will give us the limit which is x. So, therefore, what we have obtained is that under these new hypotheses, again as long as the original sequence x n converges to a limit which is some real number small x, then the weighted sums given by these numbers a n j, that weighted sums also converge to the same limit. We are going to see a special case of this result immediately, that is called the Toeplitz lemma. What we are going to do is that we are going to choose certain specific sequences, and we are going to see that the sequences under consideration will fall inside the case of this lemma 2 that we have just proved. So, here what we do, we start by looking at a sequence alpha n of non-negative real numbers, and then we will look at the finite sums of these numbers alpha j, and let us call them b n. So, therefore, we end up with a new sequence which is made up of the first n many terms from the original sequence alpha n. Now, here we assume certain regularity properties of this sequence b n. What we do is that we assume that all these b n's are positive. So, that is not a big assumption because we have already assumed that alpha j's are non-negative. So, this kind of things is expected to happen, we take it as an assumption. Then we also assume that b n's actually go to infinity as n goes to infinity. Now, we bring in this new sequence x n such that it is converging to a real number x. Now, we are concerned with again this kind of weighted sums of these random variables, and we claim that these weighted sums divided by b n, that quantities are going to again the same limit x as n goes to infinity. So, here what we are going to do is that under our assumptions, we are going to look at this double sequence, doubly indexed sequence called a I j. The way we do it is that for every integer I, we will vary the j from 1 to I, and for those values of j, we are going to look at this ratio alpha j over b I, and whenever j is strictly greater than I, we will assign the value 0. Then what happens is that summation over j equals to 1 to infinity a I j becomes 1, all the terms a I j are actually non-negative, and that is how we are going to link it to the statement of the previous lemma, lemma number 2. And hence, what we immediately observe is that by this lemma 2 part 2, we immediately will be having our conclusion by appealing to the fact that x n's converge to x in the real line, and therefore, these weighted sums which are essentially these Aij's will give you that the weighted sums are converging again to the real number x as n goes to infinity. Now, this version of this result that we have just proved, meaning the Toeplitz lemma, actually is a general version of the first lemma that we have discussed. So, what we can do is that if we choose these non-negative numbers that we have considered in the Toeplitz lemma, all of them I choose to be 1 now, and then immediately what we will have is that the b n's are the summation of first n many terms. So, therefore, these b n's are positive for all n. Moreover, they go to infinity as n goes to infinity, and finally, as long as we assume that x n converges to x, then immediately 1 by b n of the sum of these numbers which are now already these x j's j equals to 1 to n. So, that is what the terms will turn out to be, but b n's are n. So, therefore, that is going to give us this expression, this familiar expression of the averages of these original sequence, and therefore, as long as n goes to infinity by the Toeplitz lemma, it also converges to the same limit x. So, earlier we had proved in lemma 1 that if the original sequence converges, then the averages also converge to the limit x. Now, we have proved a slightly general version which is the Toeplitz lemma, which also is giving us this same framework, but here in the Toeplitz lemma we can appeal to other interesting weights. Now, earlier in lemma 1 what we had done was that we had looked at the application to almost sure convergence of random variables, and we had said that the sample averages also converge to the same limit random variable as long as the original sequence converges almost surely. Now, here I leave it to you as an exercise that since we have these generalizations of lemma 1 in lemma 2 as well as lemma 3, then figure out what should be the corresponding more general statements involving almost sure convergences of random variables. So, figure out these statements and definitely prove them. So, that is the exercise. So, state and prove the more general versions of proposition 2 that we have proved earlier, but now using the general versions which are lemma 2 and lemma 3. We can also look at another interesting variant of lemma 3 as stated here, and this we call as the Kronecker lemma. Now, here what we will consider is a slightly different set of assumptions. Here what we look at are such sequence of real numbers b n, where all the b n's are positive, and moreover we also assume that b n's are increasing. Moreover, we also assume that n goes to infinity, limit of b n is actually infinity. So, under these assumptions, if we are given that another sequence of numbers x n is given such that the corresponding series converges, then we claim that this specific sequence as n goes to infinity will go to 0. So, here what we are looking at are weights given by b j, but then at the end of the day we are also dividing everything by b n. So, that is the type of terms that we are now considering. So, in this case what we claim is that these new weighted sums will converge to 0 as n goes to infinity. Here the important thing is that the original sequence b n that we are considering are positive and they increase to infinity, and the second sequence that we are considering x j's, they are such that the summation of x j's converge. In particular, what is part of the assumption is that as long as this series converges, then the necessary condition is that the terms x n here are going to 0. So, therefore, in particular the sequence of terms x n are remaining bounded. Now, here how do you prove this result? So, what we do is that we bring it down in the framework of our earlier result, which was lemma 3, the Toeplitz lemma. So, to do that we introduce certain notations which we call as small s n. We will, for the sake of convenience of notation, that we will start with counting from 0. So, n goes from 0 to infinity, and for each value of n we are going to look at the value of S n. We take S 0 to be 0 and S n to be the sum of first n many terms of the numbers x j. Now, here what happens is that given that the series x n is converging, it immediately tells you that the sequence of S n, which is essentially the sequence of partial sums corresponding to the series summation x n, that converges, and the limit is definitely this series value. Now, since this converges, this is a number in the real line. So, therefore, we have a sequence of real numbers S n converging to this number as a limit. Now, we do some prior manipulation in order to simplify our calculation. So, we look at this summation of these terms b j x j from j equal to 1 to n. So, that is the terms we are looking at, and here we appeal to a type of summation by parts formula. So, what we are trying to do is that, so in this summation by parts, what we do is that we first look at this type of expressions. So, here what is happening is that we just have to subtract out this summation on the right hand side from b n times S n, and if we do that, then we will get back the term on the left hand side. This is a standard verification that we can just verify on its own. Now, once we have this expression for the left hand side in the form of the right hand side, what we do is that we take the term b n common from both the terms on the right hand side, and therefore, inside we end up with such an expression. Now, here what we are going to do is to focus on letting n go to infinity. Now, first of all, we introduce certain new terms. So, here instead of b j minus 1, we are going to write using these symbols. So, for any integer n greater or equals to 1, we are going to write alpha n to be this. So, here just to clarify, we are taking b 0 to be 0. All right. So, now if we write this, then here all these alpha n's are non-negative by the structure of the b n's, and moreover by the definition of alpha n's, if I add up the first n numbers, then we will end up with b n only. Now, we go back to our earlier result, and if we now let n go to infinity in this expression, what happens is that I have to only consider these two terms on the right hand side. So, this calculation was just following from the summation by parts as we have already pointed out. Now, once we have this, let us focus on the second term here. By our earlier result lemma 3, we immediately will say that this term will converge to the same limit as S n. So, this is just an application. Moreover, the first term also is just going to that limit value, which is, just to recall, the summation of all these x j's, which is assumed to be some real number. Now, once you have this, we immediately conclude that this limit what we are interested in is 0. So, therefore, that completes the calculation here. But now, once we have this, we have managed to prove this result, that for this sequence where b n's are non-negative real numbers and they are going to infinity increasing nature, and for that we have these weighted sums are going to 0 as n goes to infinity. You can again try to figure out the application to the sequence of random variables. So, if you assume that the sequence of random variables are such that summation x n is converging in the almost sure sense, then the corresponding weighted sums will converge to 0. So, that is the application of this lemma 4, which is the Kronecker lemma, and again try to write down the statement and definitely prove it. So, again the idea will be that on the complement of the null set, you are supposed to show the relevant convergence. So, in this lecture what we have seen that there are some nice elementary results in the real analysis, which can be directly applied to the case for almost sure convergence, giving us new weighted sums which also converge, and we can also identify the corresponding limits. In the next lecture, we are going to see these applications of these type of results, but using probabilistic techniques. So, in this lecture we have seen the applications of these elementary results from real analysis, but in the next lecture we are going to see applications of the probabilistic techniques, which will help us get estimates for such weighted sums of random variables. But then again we are going to use some important structure of the random variables, then that these random variables will be assumed to be independent. We are going to appeal to this independence of the random variables and get certain weighted structures or estimates for these weighted sums of the random variables. This is what we are going to discuss in the next lecture. We stop here. Thank you.